W equals mg.
Say it again.
W equals mg.
W equals mg is a specific, very specific case of Newton's second law.
F equals ma.
That's the one.
What is it?
Second law. And the third law is the equal and opposite. All right, so the force acting on it is the force due to gravity towards the middle of the planet. So why don't we just call that the positive direction? That's equal to the mass of the object, the satellite, times centripetal acceleration. What's the formula for centripetal acceleration? Chapter 8. Or if you remember that class you did.
Acceleration equals velocity squared over r.
Speed squared.
Yeah, okay.
So mv squared over r, and that's going to be equal to big G, mass of the planet, mass of the object, over r squared. So this is basically what we're working with right here, and I know it's just a bunch of letters at the moment. But we're going to simplify it and do something with it. No doubt, much to your delight. And with Thanksgiving coming up, stuff to talk about over dinner. All right, I have mass of the object on both sides. I don't care what the mass of the object is, it's going to cancel out. I got an r on the bottom here, and r squared on the bottom here, so let's just get rid of an r. Mathematically, I'm multiplying both sides by r. I get rid of that one, I get rid of one of those. So let's just write down what we have at this point. We have big G survives, mass of the planet survives, over r is equal to v squared. This r right here is the center to center distance. It's from the center of the planet to where the satellite is. And so why don't we take a common satellite we have? I hope the information's in here. There we go. Let's take our moon. How fast is our moon going? Speed of our moon. Oh, well, for v, it would be the square root of g mass of planet over that orbital radius. So that's the square root of, hey, everyone's favorite constant, 6.67 times 10 to the negative 11th, times mass of the Earth, 5.98 times 10 to the 24th, divided by the Earth-Moon radius, or distance. And that one I have to look up here, and that is 3.84 times 10 to the 8th, 3.84 times 10 to the 8th. So let's figure out how fast our moon has to be traveling. To be traveling at that distance. Units?
Just did this another one.
Anyone else get the same number? Okay, I got one.
I got, let's see, 100 times that. Let me double check what I typed in.
My crude estimate had it closer to something thousands. Well, we have, it's 2 against 1 right now. All right, so while the calculator people are doing it, those without calculators, what are the units?
Mine's doing it the other way, like the one that it was showing when you did it, what's it called? One of those-
Scientific notation?
Yeah, I don't know.
All right, so what you get?
You can't tell me. I don't even think I did. I couldn't do it
Oh.
fully. I don't know if I don't think I did a square root, so anyway.
Yeah, even that would put it off quite.
It's hard because I tried to do the
Wait,
whole
what's-
thing. I cleared it out.
Oh.
I tried to do the whole thing, but it still says error. I think it's just too much. I have to do it separately, like in parts.
The scientific notation is in 1.27 e to the 11.
Which is like what she was getting, so 1.27 times 10 to the 11th. And you did the square root,
Yes,
and you got -11 here?
yes.
I wanna
Alright.
try it again.
If you look at just the exponents, that's 10 to the -11th times 10 to the 24th divided by 10 to the 8th. 10 to the 11th times 10 to the -11th times 10 to the 24th is 10 to the 13th over 10 to the 8th, which would be 10 to the 5th. The square root of that would put it down to 10 to the 2.5, which is somewhere between 100 and 1,000. So,
Cool.
yeah, that 10 to the
I got
11th
it.
just does not seem right.
That's what I got.
You got,
Yeah, I
This
just
one?
did what she did, yeah. No, the bottom one, I really did it, let me do it. I think I probably did it wrong the first time.
did you, when you typed into the calculator, do 6.67, and you use
I did the E in the -11,
-11
yeah.
times 5.98 E24?
I did not.
I did it in parentheses, but yeah, still, that's what I did.
No, you did,
Well, I didn't do E, I did it times 10 to the power of 24, and it's still, I can try and do the E.
so 10 to the 24th,
Yeah, and
and then
then
divided by,
3.84 times 10 to the 8th,
like that?
yeah.
What's the mistake here?
Didn't square root it.
Well,
Well, no, I mean, I put it in square root, that's what.
But- what's the mistake here? Why is this coming out with the wrong answer?
The whole thing is to the,
Wait, is-
what was it? I can't read what that number is, but the denominator isn't in parentheses.
Yeah. That needs to be in parentheses,
I
because
didn't do
otherwise,
it in parentheses.
you did put in parentheses?
Yeah.
If you don't put parentheses there, you're dividing by 3.84, and then you're multiplying times 100 million.
No, I did in parentheses,
Wait,
and I got
is it
that.
dividing
This one.
those two numbers before it, is it dividing those, last two numbers before it multiplies?
I as well got the same answer.
What, this one here?
No, the one
No.
above it.
The one above it, so we got 3 now with that one.
Well, I'm wondering, if it was the way that he's saying it, then how would you be able to get the 6.7 E to -11 times that? And then you have to put it back into square root divided by, that's why it's like confusing. I don't think that made any sense, but.
Right. Hunter, you want to ask your question again? Or are you working on
I'm
yours
just
right
gonna
now?
try it for myself.
Okay.
On the one where I got 1,119, I didn't close the parentheses on the bottom of the division.
Did you use times 10 to the, or use the E button?
Times 10 to the.
And you got that?
You want me to try it with the E, maybe? it would be
I
different?
closed the parentheses, on the, yeah, closed those, and then also closed the other two. And I have, I think everything's correct. I can double check one second.
I got that top number, the 1,000.
Okay.
Yeah, but when I put it in the calculator, I don't type it all out, like, I do the 6.67 times the 5.98,
Okay.
and then I get that number, and then divide it by the 3.84 number,
Okay.
and then I put it inside of the square root.
Okay.
I
So you
take-
did it in parts.
Yeah, cause I
Okay.
feel like if I put it all in once, I'm more bound to make a mistake.
Yeah, I think you have like a more scientific calculator, cause mine won't do that. I've tried it and it just won't do it.
In scientific notation, mine is 1.01917.296 times 10 to the third power.
Okay, which would be this one right here.
Yes.
I'm still getting D1 on the top as well.
You get this one on top, you said?
Yeah.
Okay. We
This
seem to have a
might be-
consensus here. This one would make more sense given these numbers here. Next break, let's see if we can figure out what's being typed in for those
Yeah,
who
it just
aren't
might be
getting
my
it.
calculator. I might have to use a different one when we take a test or.
Well, there's usually some calculators around here that you can borrow. Unfortunately, I think this one is probably similar to yours.
Yeah,
The TI-80 whatevers, I know there are a couple of them around here. They're just not sitting on the table right now.
I'm sure if I did it in another one, I would've got the same thing as everybody else. It's just. Yeah.
Oh, and to me, the lesson is make sure you show your work.
Yeah, I can't afford an expensive calculator, unfortunately.
When push comes to shove, I have had students who have had difficulty with their calculator, and sometimes they will come up and they say, all right, what am I multiplying here, what am I dividing? And I'll type it into my calculator, but that's when the student tells me explicitly what they were trying to do. All right, so the moon is traveling about 1 kilometer per second. Yep. What are the units here?
Meters per second.
Yes, meters per second. We're trying to find a speed there. Let's take it one step further. Because why not? I'm gonna start here. What's the formula for speed?
Distance over time.
Okay. So speed is distance over time. So if I have something traveling in a circle, what is the distance called?
Circumference?
And what's the formula for circumference?
I don't know.
So it is the circumference, so 2 pi times the radius of the circle. And if something's traveling around in a circle, what is that time called? For the, let me try the wording again. If I have something traveling in a circle over and over again, in other words, I have a satellite orbiting, what is it called for the time it takes for an object to go around once?
Rotation.
That would be the more the motion it is. I'm talking about the time specifically for something to go around once.
The diameter? No, that's just.
Are you looking for a number or?
I'm looking for the word,
Clockwise?
vocabulary.
Are you saying like clockwise?
Not clockwise or counterclockwise, looking for, I guess I haven't done this word before.
Yeah, I don't know.
Period. Time for one cycle of repetitive motion. So if we're talking about the Earth going around the sun, what is the period for the Earth around the sun? Now I'm looking for a number.
Repeat the question.
What is the period for the Earth going around the sun?
365 days.
Yeah. I'm still surprised. And it's consistent that people always go for the number of days as opposed to just saying 1 year. But, I mean, both are correct. All right. So and the symbol for period is a capital T. This is the reason why I don't use capital T for tension. So this is the period. We will visit period again when we get to chapter 19. So what I'm gonna do here is I'm gonna take my formula right here, this 2 pi r over the period, and I'm gonna stick it in for v down here. So I got this g times the mass of the planet over the radius of the orbit is equal to 2 pi r over t squared. And again, I recognize it's a lot of letters being thrown in here. I am heading someplace. Again, I want you to see that it comes from somewhere. So we get g, mass of planet, over r is equal to, well, I'm squaring all of this, so 2 squared is 4, pi squared is pi squared. It's somewhere around 10, I don't need to know the exact number right now. R squared over t squared. Now I'm gonna get stuff together here. If you think about, you got a bunch of satellites orbiting the Earth. How far they are from the center of the Earth varies. How long it takes for them to go around the Earth varies. The things that are the same for all the stuff going around the planet, G is the same for all the satellites, big G. Mass of the planet's the same for all the satellites going around Earth. 4 pi squared, if the math people aren't lying to us, those are constants. So what I'm gonna do is I'm gonna get all the constants on one side, everything else on the other. I got 2 fractions equal to each other, I'm gonna go across a diagonal. So I'm gonna take 4 pi squared down, and I'm gonna bring r up. And what I'm left with, g times the mass of the planet over 4 pi squared is equal to r cubed, because I have r squared already, and I'm bringing another r along, over the period squared. Yeah, we just derived that. Give people a chance to catch up on their notes, and then I will talk about the significance of what we just did. First off, what does this mean? That means if I take the orbital radius of every satellite going around the Earth, and I divide by how long it takes to go around once squared, it is the same. That ratio is the same for every single satellite going around Earth. That's not the historical significance. But it does allow us, if I know the distance from center of the Earth to the moon, and I know how long it takes for the moon to go around the Earth, I can calculate what the mass of the Earth is. Or, why does the Earth need to be the central object? Any central object works for all the stuff going around it. So if I take the mass of the sun, I can do g times, let's see if I can get something more easily seen. G times the mass of the sun divided by 4 pi squared is equal to the radius, orbital radius of any planet in our solar system divided by how long it takes for each planet to go around the sun squared. This ratio here is the same for every single planet. And I know this information is somewhere up there, up there. This will do. All right. This particular information has an orbital period in days, so let's first off do it for Earth. So the orbital radius of Earth, 1.5 times 10 to the 11th cubed, divided by how long it takes to go around, 365.25 days. And that was meters. So if someone would be kind enough to work that ratio out. 410-677-618.1. Put the commas in there. I think I've asked this before. Anyone raised in the European tradition which flipped the commas and the decimal points? Just want to at least acknowledge that. Okay, so we're all good with commas and decimals in classic American standard. Okay. All right, units.
Meters per days.
You left 2 words out. Oh, there's a mistake here. I apologize. My formula is right. This bottom thing should be squared. So that divided by 365.25, assuming there was no mistake earlier. One second.
1,124,307.
One more time.
1,124,374.
1,124.
374. .04.
All right, so now units. I'll go back to what I was going to say when I realized there was a mistake there. You'll have 2 words out. She had said meters per day. Let's think about exponents. What are we doing over here?
Cubic.
And down here,
Square.
what are the units of the final answer?
Meters cubed per day squared.
Yep. So it's just that cubed, so meters cubed over days squared. They're not particularly nice units, and they're not particularly useful other than this one thing we're doing. That was just mainly an exercise in how to be able to pull units out of an equation if you're not sure. Now let's pick another planet. And yes, I'm gonna say blue.